All right, here we go. Practice test time. Welcome to Earth Science. Welcome back. Thanks for sticking with me today. There's a bunch of regions questions. What I do is go through random regions, find questions that pertain, and we jump onto them. So the diagram below shows the orbital paths of Earth, Mars, Jupiter, and a comet named Wild 2. What is the approximate distance between the Sun and Wild 2 when this comet is closest to the Sun? So this is it right here. This is a very eccentric elliptical orbit. And this is a question where you're going to sit there and say, geez, how on earth would I know that? How am I going to know this question? Until you look at the diagram and realize you have a reference table that when it's closest to the Sun, it's also right about at the distance that Mars is. And yes, that's a trick. That's not easy. But yes, that's what the Regents likes to do to people. So we got to practice for it. So you grab yourself your Earth Science reference table. And all we got to do is see how far away Mars is. And once you break down the question, it really is that easy. That question really just says, how far away is Mars? So you go here and you say Mars, 227.9 million, which is pretty darn close to 228. Diagram below shows the development of our universe from the time of the Big Bang to the present. So Big Bang, expanding universe, and what are these spirally shaped blobby things that are in there? Those are going to be spiral galaxies. Comets way too small at the scale. All this stuff's too small at the scale. These are looking at big things like the galaxies. Remember, there's a universe that contains a bunch of galaxies that contain a bunch of stars that have solar systems. So if we would be one star in a spiral galaxy like that. Compared to Jovian planets, terrestrial planets have what? Now, if you just finished the other video, this might be fresh in your head, but what if it's all the way till tomorrow and you're saying, well, what am I going to do? All you got to remember, the first four are terrestrial, last four are Jovian, and we are looking for terrestrial planets have what? Larger masses is not the case. Larger diameters is not the case. Shorter periods of revolution or shorter periods of rotation. It's going to be revolution. So the rotations, let's just look at it. They kind of bounce all over the place. There's not really a pattern there. Whereas these start at 88 days and they get longer, which makes sense because the revolution is going to be a longer trip around the sun. So the further out you are, the longer it's going to take to do that, even if we're at slightly different speeds. So yeah, that's that. Shorter periods of revolution. Cosmic background radiation. And again, I promise questions on this. This is it. It's just link that with the Big Bang, the origin of the universe. Our solar system formed a lot later, as did things on Earth. I know I'm going fast, but I don't want to keep you guys here all day. The theory that the universe is expanding is supported by, and again, expanding universe, redshift. They're just things that got to be in your head. And these other choices, like blue shift would happen if things were coming closer to us. That powers the sun. That's unrelated to this question. But yeah, that's the worst answer. So redshift, cosmic background radiation, stick those in your noggin, come on in tomorrow. You'll be good. By which process do stars convert mass into energy? That is fusion. Fusion powers stars. Fusion powers stars. Fusion powers stars. There will be a question. Get your points. Compared to the other planets in our solar system, Jupiter, Saturn, and Neptune have what? So again, this is going to be coming back to here. You don't have to memorize anything about planets. So what's going on with these ones relative to the others? Shorter rotations, shorter revolutions. We just answered the opposite of that, so I'm chucking that right away. Greater eccentricities or greater densities. I'm not thinking it's the eccentricity because Mercury is a really high one, and it's certainly not the densities because these densities are all lower than these ones. So that's gone and that's gone. Do they have shorter rotations? Rotation about 10 hours, about 18 hours, about 16 hours they do. So those things are really whipping. They're spinning. They spin faster than us, and they're huge. So it's kind of cool. And that's the thing with and this is going to be a theme all year, is using the reference tables and having the regions throw something at you that's like, well, Mr. F didn't tell us what planets have blah, 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 blah. I know. There's no way I could teach this course for a year and not get through all of the little minute things that you can figure out if you're clever enough to say, okay, here's the table. Let me decipher what the question's trying to say and do it. It's more about reading tables and graphs in this course than it is memorizing things. Memorize this background radiation and the redshift thing, but a lot of the other stuff is on tables like this. What two stars are most similar in luminosity? So basically, luminosity, I'm looking for two stars that are on the same, like, next to each other, left, right. Yes. Just making sure we're still recording. I'm always paranoid about that. Betelgeuse and Barnard Star. Does that work? Betelgeuse is up here. Barnard Star is way down there. They're about the same temperature, but nowhere close on luminosity. So that's not it. Procyon B and Proxima Centauri. Yeah, I like that one. Those two are next to each other, left, right. But always double check, see if there's better. Polaris and Sun. Sun here, Polaris here. Nope. Alpha Centauri and Sirius. Alpha Centauri is here, and Sirius is here. Closer, but not as good as these two are. So we go with choice 2. Bush diagram most accurately represents the relative diameters of the Earth and Mercury. So again, like scale modeling based on information, not something I would ever tell you to go home and memorize about how big are these two relative to each other. So just use the information we got. Earth's about yay big. Mercury is about yay big. So what do you say? I mean, if I'm going real rough, there's about 3 Mercuries in an Earth. So no way, it's not bigger. That's looking pretty tiny. I'm thinking I like number 1 the best. If that's about 12,000, that's about 4,000. I could buy that. All right, graph reading and answering non-multiple choice questions. Might be a first for this year. We'll see. State the name of each of the planets represented by A, B, C, and D. So we've got them by distance and period of revolution. So this is that kind of, again, that idea that as you go further away, it takes longer. We could probably honestly do this almost just by distance. Over millions of kilometers, it looks like A is roughly that one. It's got to be right, about 750. And let's just make sure with period of revolution. Yeah, that's looking right. So Jupiter. I'm not going to put you through having me write all these. I'm guessing it's just going to be Saturn, Uranus, Neptune, but let's just like double check quick. About 1429.5. Yep. Saturn. See, I'm guessing is Uranus. We're at about 2980 something years. Yes. Uranus and about 4,500 million kilometers and 160 something. Yes, that is Neptune. Okay, so graph reading, interpreting. That's again what I was saying before. That's more what this is about than the other things. What is the relationship between the sun and the period of revolution? Always answer these the same way. As the distance from the sun increases, that's always the first part. Then tell me about the second part, revolution. And what does it do? You got to figure it out. It increases in this case. Other than Jupiter, one Jovian planet, very easy. Just give me any one of those 4. Jupiter, Saturn, Uranus, Neptune. They're all good. Compared to Jupiter, state how Earth's equatorial and diameter are different. Jupiter is here, so Earth is going to be much smaller. 142 down to this. And what was the other thing they wanted? Density. Earth is more dense. Earth's the most dense out of them. So yeah, that's that. State the color and luminosity of 51. That's got to be out of something. So this is where you got to read. So 51 Pegasi, which is similar in color and luminosity to our sun. So just do it for our sun. Yellow, luminosity of 1. That'll do it. All right, getting easier. This is a freebie. Eccentricity of moon's orbit. Earth's moon. Eccentricity 0.055 Dunskies. And the life cycle of stars. Again, remember, there's no memorizing any of this. I have seen some questions on what determines the difference, and it's going to be mass. Other than that, the sequence is always given to you. Which star has the greatest probability of producing a supernova? So we need something that's like up here, that's very massive or supermassive. So out of those, I know it's not the sun. Barnard Star or Betelgeuse. Betelgeuse is way up there. Barnard Star is down here. Yeah, so Betelgeuse is the only guy that's going to be way the heck up there. Boom, boom. That's it. If you can do that, play with these reference tables a bit. know your couple of things, you're going to be sitting pretty tomorrow. Thanks for sticking with me. We'll see you guys tomorrow. Best of luck. I really hope you do well. We can really get some averages up. Take care.